Okay, this is our section about polar area. So we're going to talk about sort of the introduction here, and then you have another video that does some examples, and then we'll do a little bit more in class. So this example, or this beginning, is talking about how we would do area with polar curves. So the difference is in entirely how we think about this. So when we do regular Cartesian coordinate system, we look at the area under the curve. But polar coordinates, remember, when you graph a polar coordinate, you're graphing it by the radius, the distance it is from the pole, which is the origin, and then on what ray. So like if it was this one, alpha equals, or theta equals alpha, we're saying like on, say, pi over 2 or whatever, we want to know, or pi over, I guess it wouldn't be pi over 2, but we want to know like what that r comes out to here. So say that might be, you know, some value, whatever, like 4. And that was our r, and theta might be pi over 6. So that was our point. R theta 4 comma pi over 6. And then the way we would get to additional points is we kind of sweep this out. So you have to kind of think of it like this: theta equals alpha. If you were to sweep that across, that ray across, until it hits theta equals beta. And then it's the area for all those radiuses that come out of that. So it's a little bit different, but the idea is the same. Just like if we do area under a curve, or when we did volume, all those things, we basically divided it up into stuff that we could figure out. So in this case, we would divide it into sectors of a circle. So we would take and have rays that would come out and would hit here, and then we would have a sector that would be part of a circle there. And then we would have another one that came out, and we would use the sector of a circle that connected those two things, and that would be the area that we would use to approximate all these different little things. So we would have these sectors of circles, and then those would be used to estimate it. And then just like everything else we do, we want to have infinitely many of those. The more and more and more we have, then the more that becomes the exact area. So a sector is like a slice of pizza. So it's like if we had 4 slices of pizza here that were long and thin, it looks like, that we were trying to use to approximate this particular region that's in green, okay? So again, what we would do is do more and more and more and more and more. Well, the area formula for a sector of a circle is given by area equals 1/2 theta times r squared, where theta is in radians. Remember, in calculus and math, we're in radians, 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 okay? So that's this area of a sector of a circle. And then instead of being like x equals 1 to 3 or y equals 2 to 4 or something for our range, for our integral, we're doing it from, we're sweeping out from alpha equals, or from theta equals, or alpha to theta equals beta. So we're kind of sweeping that out and covering this area, okay? So that's how we get the formula. So the formula is actually super easy. It's 1/2 r squared. That's what I'm going to remember. Area of a polar region is 1/2 r squared. And then you go from alpha to beta. So that's the radiant, or the ray that comes out and goes alpha to beta, that sweeps it out. So very simple formula, really. Okay, so let's do this graph. So most of the time on the AP test, you're not actually required to know what these graphs look like. But just like anything else, it's really helpful if I do kind of know. So even though probably this would be on a calculator question where you could graph it by yourself, I'm going to go ahead and go by what we've been practicing so you know what it is. So it's 2 plus 2 sine theta. So that means it's a cardioid. It might have a loop, might be flat on one side, but it's that type of shape. Because A and B are the same, that means that it has the, it just dips in. So that means it's going to look basically like this, and then be symmetrical over here. And that's terrible, but it's going to be basically like this, where this is 2, and so this is -2. That's how far out we would go. Now, I can figure some things out by, remember, just plugging some stuff in also. So if I need to get an idea of a graph, I can plug in things. So let's start with theta equaling 0, which would be the positive x-axis, like that exact place. If theta is 0, I'm going to have sine of 0, which is 0, plus 2. So I'm going to get that r is 2. If I look at another value of theta, and we're only going to pick values of theta that are nice, and then just pick some more in between if we feel like we need it. So I'm going to do pi over 2. So sine of pi over 2 is 1, times 2 is 2, plus 2 is 4. So r will be 4. So this will be 4. And then if we pick like theta equals pi, well, sine of pi again is 0. So you're going to get r equals 2, and then we can sort of see that. So in order to get the area bounded by this graph, it's looking like that we will go from 0 to 2 pi to trace the graph once. Okay, so if I want the area, then I'm going to integrate from 0 to 2 pi. Just because remember, on polar, you sometimes might go over and over and over. Okay, well, here's how simple it is. Area equals 1/2 the integral from alpha to beta. Well, we just said we'll go 0 to 2 pi. Now do make sure that always goes from smaller to larger. Like, that has to make sense. And then it's of r. Well, what does r equal? R equals 2 plus 2 sine theta, whole thing squared, and then d theta. And then I'm going to do this question by either multiplying all of that out and doing a big mess, or most likely it's a calculator question. Okay, so it's either going to probably just be put this in the calculator, or it's going to be set it up but do not integrate. Okay, so we're not going to spend a lot of time simplifying those because it's unlikely that you will ever see anything when you do that. You go through this whole process and you end up with 6 pi. And that's the area inside that. Okay? So, most of the time, your graphs, if you're doing polar, they will give you the graph, so they'll draw it. They'll probably tell you r is 2 plus 2 sine theta, but then they'll also draw the graph. So all you'll have to do is figure out the starting and ending points and make sure you're not tracing the graph more than one time, which is something we kind of looked at. So you'll see in the next examples how we can kind of figure out a starting and ending point and that kind of stuff. Oh, and by the way, mentioning this too, could I do 0 to pi, right? Because when I plugged in pi, didn't I get a radius of, oh, not 0 to pi then, sorry, I'm doing the wrong thing. That won't work. 0 to pi wouldn't be where it was symmetrical. Where it would be symmetrical would be where this started around to that point. Well, that point's at pi over 2, so I bet you this bottom one is at 3 pi over 2. So if I do 3 pi over 2 for sine, I would get -1 times 2 is -2 plus 2, I would get r is 0. So that is in fact that point. However, I can't integrate from 3 pi over 2 to pi over 2. That wouldn't make sense. So I'm going to need to call this negative pi over 2. And if I go from negative pi over 2 to 3 pi or to pi over 2, I'm going to get half of this region. So an alternate way I could do this is using symmetry. I could do that area equals 2 times 1/2 of the integral from negative pi over 2 to pi over 2 of that r squared d theta. Okay, so I could also use symmetry. The caution I will give you is you can't call that 3 pi over 2. You have to call it negative pi over 2. Okay, so because it has to go from smallest to largest. So there's some caution in that. You'll see that in some other examples. So when you watch the next video, you'll see some more area, and then we'll do a couple in class to further answer some of those questions and figure out how to do polar area. Formula, super easy. 1/2 r squared d theta. So remember that.